Hello students, today we will discuss about multivariate functions, limit and their continuity. At first, I recall the definition of mapping. Suppose you are given two non-empty sets A and B. Okay? A mapping F is a rule that assigns to each element x in A to a definite element y in B. Okay?
Now I will give the definition of a multivariate function. Let us consider the Euclidean plane or the xy plane. We write xy plane as symbolically R2. Okay? The R2 is nothing but the Cartesian products of R cross R, where R is set of all real numbers. Let D be a non-empty subset of R2, then f d2R is called multivariate function, and we write f as symbolically f of x, y is equal to z, where x, y belongs to D and z belongs to R. X, y is typical element of R2 and z is real number. But why is it multivariate? See, here x and y are totally independent variable, okay, and z nothing but a dependent variable. So if we change the value of x and y, the function takes different z from the real line. That is why we call the function f is multivariate.
Now I give an example of a multivariate function. Okay. F of xy is equal to x square plus xy plus y cubed. This is a multivariate function, and you can see that if we change the value of x and y, then this is totally a real number. Okay, and here the domain of the function is totally R2. That's it. Now I will give the definition of limit of a multivariate function. So I write here. Definition. See, let D subset of R2 be a non-empty set. See, whenever you will define a function, you have to remember that you have to take a proper domain for that function. Okay, without defining domain, a function is not valid. That is why I take here the domain D. Okay. Now we will take a point A comma B or there. Okay. See, let A comma B be a point in R2. Let A comma B be a point in R2. May or may not be in B. This is the vital line in this definition. Okay. A comma B may or may not be in D, but but a comma b is very close to d as much as you can. You have to take the point a comma b where we estimate the limit of the function is very close to d as much as you can. Okay? Let x comma y belongs to b and x comma y tends to a comma b in any manner. In any manner. This is another important thing, this definition. What is meant by this underline? See, here I draw the picture. Okay, suppose you have the domain D. You have the domain D. As I said that the point a comma b may or may not be in D, so I consider the point here, which is a comma b. Now I consider another point in D and tending this point to a comma b in any manner. In any manner means you can travel to this point through this path, or you can travel to this point through this path. Okay? So here now we said f has a limit L where L is a real number. We said f has a limit L at a comma b if. Now these are very important things in our definition. If for each epsilon greater than 0, that means positive epsilon. If for each epsilon greater than 0, we can find a positive delta, that means delta greater than 0. If for each epsilon we can find a delta greater than 0, such that mod of f of x comma y minus L less than epsilon whenever this see x minus a whole square y minus b whole square less than delta square. Okay, mind it, this delta is dependent on epsilon. Okay, at first we choose epsilon, then we can find delta, and that delta is entirely dependent on F shadow. Okay. Now I will explain this inequality to you. See, we all know that the equation of a circle centered at A, B having radius delta is x minus a whole square y minus b whole square is equal to delta square. And the picture of this circle is this. Here is the center and here is the radius delta. This equation is satisfied by those points which are lying on this curved line. Okay, this is our circle, not this portion in this picture. But if we replace the equality sign by less than sign, okay, if we replace the equality sign by the less than sign, then this inequality is satisfied by those points which are lying in this portion of the picture. Okay, and this is called a disk. This is called a disk in R2, and this is the equation of a disk in R2. Okay, now I erase this picture. So here our domain B, and since our codomain is a real number part, okay, then this is our real number. Then this is our real number, and assume that this is the point L or limit. Okay, so here see that we have to approach the point A comma B. We have to approach the point A comma B. Okay, so here the functional value is very close to L. The functional value of F is very close to L. So our function will approach L in this way. Our function will approach our L in this way, such that this is our disk. This is our disk, and we approach the point in this way. Okay. If we approach the point A comma B in this way, then our functional value of F is approaching L in this way. Okay, this is the concept of limit. This is the concept of limit. Now I will give definition of continuity of multivariate function. Okay, so as I said that to define a function, we have to define the domain of the function at first. Okay, so I wrote here, let D subset of R2 be a non-empty subset. Okay, and let F be to R be a function. Now see that in the definition of limit, the point at which we have to estimate the limit, the point A comma B, may or may not be in the domain, but it has to be close to the domain. Okay, but in the definition of continuity, we have to take the point at which we have to determine the continuity of the function has to belong in the domain. Okay, that I wrote here. I am writing here that let a comma b belongs to D. Okay, then f is set to continuous at a comma b if for epsilon greater than 0 we can find delta greater than 0. Delta is depending on epsilon such that f of x comma y minus f of e comma b less than epsilon whenever x minus this is the definition of continuity of f at a point. Okay, now if the definition is satisfied by f for each point in the domain, then we call the function f is continuous on the domain. Okay, if f is continuous at each point in the domain B, then f is continuous on D. Okay, now I will do some problems about limits and continuity. Okay. So our first problem is prove that limit of the function xy equal to 0. So in this type of problem, we have to use a very well-known inequality. Okay, these inequalities is very useful tools to solve this type of problem. Note down this inequalities. Okay, answer. At first, we have to assume a positive epsilon. Let epsilon greater than 0. Epsilon greater than 0. And we observe that what we observe? That this the modulus of this fraction is always less than or equals to 1 because this x square minus y square is always less or equal to x square plus y square. Okay. Since x square minus y square less or equal to. Okay. Now we will apply the definition of the limit. So f of x comma y minus 0 is equal to, and write the function zero, and now I will use these inequalities and this observation. Okay, equal to at first now
Mod of x is replaced by root over x square plus y square, and mod y is replaced by root over x square plus y square, and the fraction is replaced by 1.
now the final step is less than epsilon, whenever x minus 0 is less than delta square, where delta is root over epsilon. Okay, where delta is root over epsilon. So limit x comma y tends to 0 comma 0. Okay, is equal to 2. Very easy. Okay, just you have to understand the definition and understand the pictorial view of definition, which I have shown to you, and these inequalities, you have to remember these inequalities and this observation, and the problem is very easy. Okay, so I will erase the board. Now, in our problem 2, I have taken the same function which is taken in problem 1. Okay, but here some difference, that is, we define the function this for non-zero points and 0 for 0 points, and we have to check the continuity at 0, 0. See, in limit, when we are checking the function of the limit at some points, then the limit, the point at which we have to estimate the limit, the point may or may not be the domain. Okay, that is not our concern. But in continuity, the point at which we have to check the continuity of the function, that point must be in the domain. That is why we define here the function at the point 0. Okay, and the procedure is same as the problem. So after this, I am writing this. So f of xy is Now I will do some problems in which limit doesn't exist. Okay. Problem 3. Problem 3. Show that the following limits do not exist. Okay. 1. Limit to x, right? Limit okay. So answer. At first we have to write some lines. In each case, we will show. In each case, we will show that for two different modes of approach of this is common here. The limits differ and hence the limit will not exist. Okay, I have to change the pen. Okay. See, in the definition of limit, I have said that we have to approach the point at which we have to estimate the limit of the function in various manner. Okay, in various manner. Suppose this is the our 0,01 and this is the arbitrary point. Okay, so we have to approach the point in various paths, But whatever the path you may choose, the limit will always same. Okay, but for these functions, if we follow the different paths, then the limiting value of the function at that point will differ. Okay, so our problem 1 is, see, if we choose the path y equal to mx. What is y equal to mx? See, this is our origin. This is our origin. This is x-axis. This is y-axis. And this is our origin because we have to estimate the limit at the origin here on here. We are choosing the path y equal to mx, and what is y equal to mx? This is a straight line passing through the origin, okay, and m is the gradient of the straight line. That is why the line are this and this and this and this, okay. Each lines have different gradient. So limit to xy to xy, and here you have to write the board and approaching okay, approaching it along y equal to mx. You have to write this line in this way, okay. So limit. Now see that if we put the y equal to mx in this function, then the function will be the one variable function, okay. So and we will write the limit as x tends to 0, okay? X tends to 0 and 2x y equal to mx, and here x square plus x square m square. Now x square is common, so if see that x square to be cut out, okay. So the limit of the function is entirely dependent on this, and this expression is depending on m. See, this expression is entirely dependent on the values of m, and m takes various values because m is gradient of the straight lines passing through the origin, and that is why the limiting value of this function at 0, 0 is different at each value of m, and that is why the limit of this function at 0, 0 doesn't exist, okay. So you have to write this. So fx, so limit rather than exist. Okay. problem number 2. Problem number 2. Let x, y tends to 0, 0 along the path x equal to my cube. Okay, x equal to my cube. Then limit y tends to 0 see y to the power 6 will be removed. Okay, then our expression will be this. Okay, this is no is different for each different values of n. Okay, this is different for each values of n. So limit of x comma y does not exist. Okay. Now this problem is very similar to our problem number 2, I think. So this will be homework. I will do 2 and 3. So write this problem and write this board. Now our first function is f of x y is equal to plus x equal to y. Letting x, see, x minus y is equal to m x is cube. Okay, this is the path in xy plane. So limit what is the function? Function was x is cube. Okay, x is cube plus x minus 10 x is cube whole cube, okay, by 10 x is cube. You have to calculate this, okay. And this will be 1 plus two by 2 by. So it is an entirely dependent variable. So limit of the x okay. Now for number 3, let allow see x minus y m x to the power 4, okay, x to the power 4, and the limit f of xy is 2 by m. You will calculate this in order to okay. So I will choose the path. I have choose the path and calculate this. So